The question I have is, could you explain why clays are cohesive but not sands? To answer this question, first I need to talk a little bit about what is called specific surface. So let's go ahead and talk about specific surface first, and then we'll come back and address the question of where the cohesion comes from in clays. Let's look at the relative sizes of common clay minerals. Let me call the thickness as H and the approximate diameter as D. Here's a list of these quantities for kaolinite, illite, and montmorillonite. You can see montmorillonite is the smallest of three, both in terms of the diameter and the thickness. Let's compare these with the dimensions of a typical sand particle. Approximating its shape by a sphere, a typical diameter is about 0.5 millimeter. In the earlier slide, I talked about the soil type purely based on their particle size. We had boulders to clay, with boulders having the largest particle size to clays having the smallest particle size. And we had coarse-grained soils consisting of boulders to sand and fine-grained soil consisting of silts to clay. There is yet another way to classify the soil, and this is based on their cohesive properties, and some soils are cohesionless and the others are cohesive. It turns out that all coarse-grained soils are cohesionless, and clay is definitely cohesive. Silt kind of fall in between, sometimes exhibiting cohesive property and sometimes behaving like a cohesionless soil. So is there a quantity that could tell us a soil could be potentially cohesive? It turns out there is a quantity called specific surface. There are a couple of ways to define this. This is one way. Specific surface equals surface area divided by mass. Basically, it tells you how much surface area you have in a given mass of soil. Here I calculate the specific surface of a typical montmorillonite and sand particle. Actually, the thickness of a basic montmorillonite sheet is 1 nanometer. But a particle consists of a few of those, and therefore here the thickness of the clay particle is listed as 3 nanometers. But for my calculations here, I'm going to assume the thickness of a basic clay mineral or basic montmorillonite clay mineral, which is 1 nanometer. Assuming a specific gravity of 2.7, the density works out to be this, 2.7 times 10 to the 6 gram per meter cubed. Because the thickness is so small compared to the diameter, we can ignore the surface of the edges over here. So the total surface area is approximated as 2A, where A is the area of one side of the plate. The mass of the clay particle is AH times rho, where AH is the volume and rho is the density. So after substituting these numbers, you end up with the value of 740 meters squared per gram for the specific surface. Actually, the thickness of the clay particle is a little less than 1 nanometer, and this is the number that you will see in books and papers. And if I repeat these calculations for this sand particle right here, you will end up with the value of 0.012 for the specific gravity of this typical sand particle, 0.012 meters squared per gram. So here's the comparison of the two values, and therefore this clay particle has a much larger specific surface than this typical sand particle. It turns out that the cohesion is a surface phenomena, and this is the reason why clays have cohesion, whereas coarse-grained soils like sand don't. So let's address the question of where the cohesion comes from in clays. This is an area where my students and I did some research over the years. It turns out a clay particle is negatively charged on its surfaces. So let's say the surface charge density is sigma. And I'm going to take this particle and put it in water. And we know water usually contains some kind of salt, Let's just say we have sodium chloride in this water. And of course, sodium chloride ionizes into sodium ions and chloride ions. And this is what happens. The surface of the clay particles attract cations and repel anions. And so the ions in the water become redistributed around the clay particle. Now let's say we put two particles close to each other, like in this picture right here. Due to the redistribution of the charges between the two particles, a force develops in between the two particles, and this force is repulsive in nature. And it turns out this force is a function of all these variables, and the force decreases as the function of the surface separation or particle separation, like shown in this picture right here. There is no such negative charge on the surface of a sand particle, and as a result, the repulsive force between two sand particles is zero. Now let's talk a little bit about attractive forces between particles. When you place two clay particles close to each other, like in this picture, molecules from one particle interact with the molecule from the other particles. And this brings about a force between the two particles. And this force happens to be an attractive force called van der Waals attractive force. The magnitude of this force is a function of the particle separation d, particle dimensions, and a few other things. The van der Waals attractive force also rapidly decreases with particle separation d, as shown in this picture. But if you take two sand particles, the distance between molecules are so large that the attractive force is basically zero. Now we can explain the origin of cohesion. If I take a small sample of clay, there are millions of clay particles in there, and they are arranged in a very complex manner. So it turns out that in some pairs, the attractive force dominates, leading to a cohesion. In other words, if you try to separate the two particles, the attractive force will resist it. In other pairs, the repulsive force dominates, and there's no cohesion between the two particles in such pairs. Because you always have a lot of these, on the net, there is cohesion between particles. And this is the origin of cohesion. And since there is no repulsion or attraction between sand particles, there is no cohesion between sand particles. And by the way, these forces are collectively called the physico-chemical forces between particles. The next question is there any friction between soil particles? The answer is yes. There is friction between clay particles, and there is friction between sand particles. So in clays, in addition to these forces, which are called the mechanical forces, we have the physico-chemical forces. On the other hand, in sand, we have only the mechanical forces. There are no physico-chemical forces.